So today we are going to discuss multi-degree of freedom systems in our ongoing course on helicopter dynamics. I am Dr. Anjan Ganguly. So let us look at a simple multi-degree of freedom system. So we will consider a 2 degree of freedom system to make it simple, and for us to derive the equations you can very easily extend it to more degrees of freedom. So here we have two masses which are connected by a spring, and then there are further springs here which link it to some support. And these masses are on rollers, so there is no friction. They are free to move in this x direction. Now, essentially, if we think about how this thing is going to move, we could pull it by some quantity x1 and release it. And then both these masses are going to move independently. So we can visualize that there will be a motion where both of them move in the same direction, or they may move in two different directions, as the case may be. So in general, we can say that when we have two masses like this, there will be 2 degrees of freedom for this system. And these degrees of freedom are described by x1 and x2, as shown here in this figure. So this is a 2 degree of freedom system, with the degrees of freedom being x1 and x2. So now the first step in solving any such problem for its natural frequencies would be to draw the free body diagram. And to do that, we can consider a case where maybe x1 is greater than x2. So this spring is basically compressed. And so if this spring is compressed, there is going to be a force acting like this. That is going to be k x1 minus x2. This is going to push this mass here. This is going to push this mass here. Now correspondingly, there is going to be a restoring force kx1 here. There is going to be a restoring force kx2 here, because this mass is going in this direction, so there is a force here, and so on. Now, as far as the forces due to the mass is concerned, remember that x1 is in this direction, so the force mx1 double dot acts in the reverse direction. Similarly, x2 is in this direction, so the force 2mx2 double dot acts in this direction. Remember, this mass is 2m. So these are essentially the two free body diagrams for these two masses, and each of these must sum to 0, so we can write the governing equations of motion. So let's look at this one first. So you get mx1 double dot here plus kx1 minus x2 here plus kx1 here equal to 0. That's the first equation. The second equation would be 2mx2 double dot here plus kx2 here minus kx1 minus x2, because this force is acting in the reverse direction. So again, this sums to 0. So these are the two governing differential equations for this problem. You can see here that they are coupled in the sense that there is an x2 in the first equation and there is a x1 in the second equation. So now we are going to look at what is widely known as normal mode vibration for this 2 degree of freedom system. So this particular phenomena is of great interest in vibration theory, and essentially what we are presuming here is that each mass goes through harmonic motion at the same frequency and passes simultaneously through the equilibrium position. So mathematically what it means is that we assume x1 and x2 to have the same frequency here given by omega, and a1 and a2 are the amplitude of these motions. Now we are going to plug this particular set of equations into our governing equations and then see what happens. So that's our governing equation here. In this governing equation, I plug these two here. Now remember that if you take the second derivative of this, you will get a negative sign because of the presence of an I square term. Remember, I square is minus 1. So we can write the first equation in this form. There will be 2k and there will be a a1 in place of x1. There is a negative ka2 And as far as the mass is concerned, there is a negative sign because of the presence of I square, and you get the omega squared term because of the second derivative of x1, which you take here. So that is the first equation which you get. As far as the second equation is concerned, again you would get a negative term in mass here because of the I square, and the frequency square is also present. You have a term involving 2x2, so that becomes 2k here, and you have a term involving minus kx1, which becomes minus ka1 here. So these are the two equations which we get. And now we are going to think about these two equations. Now, clearly, we want these two equations to have a non-trivial solution. There is a trivial solution, that is a1 is 0 and a2 is 0. And that essentially means that there is no motion. So that's not something which is very interesting for us. So now, if you remember simultaneous equations, you know that if these two equations are going to have a non-trivial solution, then the determinant of the matrix here should be 0. So essentially we take the a1 and a2 out, we can form a matrix. So if you look at it, the coefficient of a1 would be this here. You can see this here. For a2 is minus k here. For a1 is minus k here. And for a2, once again, you get this coefficient here. So you get this coefficient here. There should be 2 here also. So this should be set to 0. Now, when we set this to 0 and we solve it, and let us put the square as lambda, we get a characteristic equation in this form. And this characteristic equation is something which has two roots because you have 2 degrees of freedom here. And so these roots are going to be lambda 1 and lambda 2. And if you further simplify these forms which involve root 3 and so on, you get first root is 0.634 k by m, second root is 2.366 k by m, and clearly you can see dimensionality is good because k by m is a typical dimension of the frequency square. So again, remember that the frequency square is equal to the lambda here. So essentially what we obtained now is that we have found the two natural frequencies of the system. So for the 2 degree of freedom system, there are two natural frequencies given by these two values here. Now let us turn to the mode shapes. So let's again get back to these two equations. And now what we do is we take a ratio. We cannot solve for precise or absolute values of these quantities here, but from the first equation I can write a1 by a2 is k by this value here, and from the second equation I could write a1 by a2 is this value divided by k. So essentially these two equations yield to me the amplitude ratio, and there are two values of this amplitude ratio which I can get. So let us try to find out the first mode shape first. So to just keep in mind, I have put these two frequencies here, which are the natural frequencies of this 2 degree of freedom system. Now I take the ratio of these two A values and I take the first frequency here. So this is the first frequency. And now what I do is I take one of these values. Now you can take the second value also, but let's just take the first value here. And then we plug in this particular value of frequency square into this here. So once you plug this in, this being k by m, the m would cancel off. You would have a k present in the numerator, a k present in the denominator. There would be cancellation of k, and finally you'll get a number that is 0.731 in this case. So that's the ratio which will lead us to the first mode shape because it corresponds to the first or the lower frequency. So we typically refer to the lower frequency as the first, the next one as the second, and so on. Now we look at the second mode shape. So again, the same ratio is given here. The first two frequencies are put here. And now we are looking at the second frequency, which is here, the 2.366 k by m square root. So now we know the frequency square. So we take one of these ratios and we put this here now. So here we have put 2.366 in this location, and after some simplification this leads to minus 2.73. So this is a negative value. You can see here that this is going to be a negative value in the denominator. This yields a negative ratio here. So for the second mode shape, the A1 by A2, and this simply means second mode shape, is minus 2.73. So these are the two ratios we have obtained, where 1 means the first mode, 2 means the second mode. Now, like I mentioned before, we can only find the ratios of these amplitudes. Therefore, what is done is that one of these can be set to 1 and the second number can then be found. So let's set A2 equal to 1. So if we set A2 equal to 1, then the first mode shape would become 0.7311. So what I have done here is I have set A2 equal to 1, and then A1 can be calculated to be 0.731. So this ratio can be expressed like this. Similarly, phi2, I would have A2 equal to 1 here, and so A1 would become minus 2.73. So that's the second mode shape. Now there are further ways of simplifying this. Some people like to take this and divide by the norm of this value and so on. So you can have many different normalizations possible for the mode shape, but essentially they have some kind of normalization typically being done so that it is presented in a compact form. So these are sometimes known as normal modes. Now the normal word we'll discover later. Essentially they are normal because they are perpendicular. So that's something we are going to discuss in a later lecture. So again, just keep in mind that these two are the mode shapes for the problem. So what does that physically mean? The first case, what it means is that x2 is going by the amount 1 and x1 is going by the amount 0.731. That's amplitude 2, that's amplitude 1. So clearly the motion is something like this. And what it means physically is that x1 is moving in this direction, x2 is moving slightly more in this direction, but both are moving in the same direction. Now the second particular case, A2 is moving by 1 and A1 by minus 2.73. So here this one is moving by amount 1, this is going in this direction by a larger amount minus 2.73. So that's the second mode of vibration. So these are the two natural modes or normal modes or modes corresponding to the two natural frequency, and these are often referred to as mode shapes. So this particular shape is referred to as a mode shape because they essentially tell you the type of motion which this body is going to take depending on the frequency you are considering. So this motion corresponds to the first frequency 0.634 k by m. This motion corresponds to the second frequency 2.366 k by m. Now we will take these two equations and we will put them in matrix form because that's how typically you generalize this problem, and you can then easily think of this as a multi-degree of freedom system. So we have used 2 degree of freedom here to make it simple for us to do this problem, but you could very easily use one more mass x3, another mass x4, and you could have multiple degrees of freedom like so on. So each of those masses would have an x with it. So this is the equation we had obtained. Now if we put it in matrix form, we take the x1 double dot, x2 double dot, bring it here, and then we get m and 2m as the components of this diagonal matrix. We take x1 and x2 here. So for x1 I would get 2k, and for x2 I would get minus k. That's what you see here. From the second equation I would get, for x1 I would get minus k, and for x2 I would get again 2k. So interesting is that both these stiffness and mass matrices are symmetric, and that is a very interesting fact you see in most systems. Now this equation, we don't need to write it out each time. We will have the same structure of the equation, so we can write it as a general equation of the form mq double dot plus kq equal to 0, where m and k are called the mass and stiffness matrix, and q is a vector containing the degrees of freedom of the system. So in this case, degrees of freedom is x1 and x2. In a more generalized case, it would be x1, x2, x3 all the way to xn. So now let us look in very general terms. If you have a generalized multi-degree of freedom system and you find the governing differential equations, you can obtain the matrix equation of this form. You can presume Q to be a harmonic motion and substitute here. If you do that, you get this problem, also known as a general eigenvalue problem. So there should be a bar here. And then you essentially find the eigenvalues of this problem. There are many solvers which will just give you this. And then the frequencies or the natural frequencies of the system are going to be the square root of these eigenvalues. So one of the interesting things here is that you don't even need to do all this formulation. If you have a typical system and you obtain the stiffness and mass matrix, you can immediately find the eigenvalues of the system, and these will be the squares of the natural frequencies of the system. For our problem, it was 2 degree of freedom, so essentially we will have two natural frequencies for that system, which we saw by deriving it in scalar form by hand. Now typically you have a n degree of freedom system, so this problem will essentially be solvable, and the eigenvectors of this particular problem, that is the phi here, represent the mode shapes. So that's something which also comes out to you by simply solving this mathematical problem. So essentially the physical problem has become a mathematical problem, and it can be very easily solved in computers. MATLAB may actually give you functions to do this. Now sometimes people like to deal with a more simple problem. So we could take this equation here, mx double dot plus kx equal to 0, and we'll just drop these brackets and all, keeping in mind that these are all matrices and vectors. And so if I pre-multiply this matrix by inverse of m, I get this matrix here, this simple equation. Now this equation, if you look at it closely, is in the form x double dot is minus ax. So this particular matrix A, this is a very interesting matrix. It is also sometimes known as the system matrix or dynamic matrix, since all the dynamic properties are defined within this matrix. So A would be inverse of m into k, and essentially this contains the mass properties of the system, the stiffness property of the system, and this matrix, system matrix or dynamic matrix, essentially captures the complete system. Now you could write this previous problem in this form if you presume harmonic motion, and therefore what this tells you is that you have to find the eigenvalues of A, and those would give you the squares of the frequencies, and the vectors would give you the mode shapes. So this is a very simple problem. You can solve this using any solver or any higher level programming language such as MATLAB or Python, and you can get the natural frequencies of the system. Now it does not matter whether you got this from a typical free body approach like we did today, or you use some more complicated computational mechanics method to do this. So you could use FEM, for example, or some different discretization methods, as long as you get the mass and stiffness matrix and they are in a good form in terms of symmetry and positive definiteness, you can very easily calculate the natural frequencies and the mode shapes of the system. So that essentially culminates today's video on multi-degree of freedom system. I hope you are enjoying these lectures. Please subscribe to my channel if you are. I will see you in my next video.